Okay, today we will look at the problem number 72, which is edge distance. Before this was marked as hard, but now since it has become very popular now, this has become quite medium, and this has become a basis of many other problems. So let's look at the problem. So we are given two words, word 1 and word 2. We are asked to change word 1 to word 2 in minimum number of operations. So what all operations we can do? First is insert, second is delete, and third is replace. Let's look at how we can do these three operations in this example. So here we are given HORSE. So how can we change this into ROS in minimum number of words, in minimum number of operations? So what we can do is we can remove this, and change this H to R. Now this will become, this will be R. We have removed this, remove this. Now in three number of operations, this has become the second word. We can show that this is the minimum number of operation which will be required. So let's look how we can build upon a recursive solution to get the answer. Since we have three operations, there are multiple, and we have to check all possible scenarios. Recursion is a way to go through. So let's take a horse and ROS as word 1 and word 2. We can go from first or last, but let's look at from last in this case. We will look at the last element in the both. So here it is E, here it is S. We will look that if this matches, then there is no need to change it. We can go to the next index. But since here it doesn't match, we have to do one of the three operations. So let's do all three operations. First we will look at insert, then delete, then replace. What will happen in insert is that we will insert the element S in the horse. So here we can see we have inserted the S, and we have made these two element equal. One more thing to notice is how the indices will change here. So since you have inserted S here, what we have seen is we can move this pointer now to the next one because these two have matched. So let by doing that we will reduce the index of j to 1 in insert and make the uh, I index same. Means it will remain same because we are still at the same index for I. Now let's look at the delete. In delete, what we do is we delete the E part and then move one index before. So here we can see we have deleted the E and moved one index before. We have decreased the count of I and and let the J remain same. And the last operation is replace. In replace, we can replace this E with S, and since both of these condition now will be satisfied, we can reduce both I and J by 1. We can repeat this step, and let's quickly look how horse is replaced to ROS in this case. So let's first delete E, then we get HORS. Now, since this last element matches here, we can just remove S from here, and we will get directly to HOR. Now we see that R doesn't match and we will remove S also from here. So we will move one index, one index before. We will remove this R and S. Now let's look at this case now. Does O and R match? No. Then what we can do? We can do either the three of this step. So optimal in this case will be delete. We remove R, we get HO, and now Does O and O match? Yes, it does. So what we can do is we can delete O, we can move the pointer to R, and here uh, we have just one letter to compare now, H and R. Now we can do either of the three operation, but we can see that replace will give us directly R, and this would match this solution, and hence we get that in one, two, in one operation we get HORS, in the second operation we got HOR, and in third operation we got H, which we replaced with R. So in total three operations we got our final answer. Now let's look at the case that if all of the last three elements were replaced by ROS. Now index has moved to this position, which is -1. Now what will happen? So since we are given that we can delete an element as an option, we can simply remove these all. So uh, we, so we can just, for the number of operation, we can just add the remaining number of letters in word 1, so that would be 2. So in this case, since uh, we have replaced these two uh, because it was HORSE, we have replaced these two with OS, so number of operations here are 2 plus, since we need to delete this, okay, plus 2, so total number of operation will be here 4. So I will just give in the edge case when the index comes to the -1, what we will do of the remaining part of the word 1. Okay. This will give us a recursive way. We can also memorize this to get an optimal solution. Now let's look at the tabulation solution. So what happens is tabulation is to just represent the same kind of operation which happens in memoization and do it in sub-problem manner. So let's say that we start by taking word 1 and word 2 as empty. So do we require any number of operation to change word 1 to word 2? No, it will give us 0. Now let's take word 1 as R and word 2 as R and word 1 as empty. Now just tell me what will be the number of operation. It will be one delete operation, and this will give me the word 1 as, sorry, in since we need to make word 1 to word 2, it will be just one insert operation R, and then we will get uh, the answer R. So we just need to give one here as the right answer for this question sub problem. Similarly, we can do this. Now let's look at the case when we are given H and R as word 1 and word 2. Now what we need to do is to check all the possible situation, uh, that is insert, delete, and replace. So how we can look for replace? So as we have seen here, that in replace, what we used to do was to decrease I and j by 1. So in this table, we can look that I and j, if reduced by 1, will give us a element which is already there in the table. So we need to just look at this table and add 1 to it. Why 1? Because we are doing replace here. This will add 1 to the total cost of operation. So if these two would have matched, we would have just looked at the 1 I minus 1 j minus 1 1th cell. But if this doesn't match, then we have to look all three possible cases, which is insert, delete, replace, which is the minimum. We will take that and then add 1 to it. So this will give us now the index at the final position will give the answer.
let's look at the time complexity of tabulation. In tabulation, since we are iterating row and column wise, it will be order n cross n. And also, what will be the space complexity? It will again be order m cross n because we are creating 2D array of size m cross n. Okay, now let's look at the time complexity of recursion. So at every step we have three possible ways to go. So it's 3 to the power. In worst case, what will be the size of the depth of the tree? It would be total length of the total word 1 and word 2. So it is order 3 to the power n plus n in recursion. And what if we memorize it? In memorization, we create a 2D array of n cross n. So we will not be going to the steps which have some for which you know the answer. So it will reduce to order n cross n in time complexity. And for space complexity, it will be n cross n because we are taking 2D array plus order n plus n for the recursion step. That's the depth of the tree, which maximum it can go. That's all. Let's look at the code now.
Solution. First we will look at the recursive solution. For the recursive solution, let's make a function which will recurse through all the possible cases. In this recursive function, we should store the index of the words and then the words. Word 1 means word 2. Now let's look at base case afterwards. Now we will check that if word 1 I equal to word 2 j, if the characters at these positions are equal, then we need only to move one step back from both word 1 and word 2. We will also declare our integer answer as an answer, and we will store the result here by recursively calling the previous case, which is I-1 j-1 for word 1, word 2. And what if the both of the last two elements in the word doesn't match? So if we add index I, index j, if the word doesn't match, what will you do? We will do one of the three cases, which is replace, insert, insert or delete. So as we look at the solution, how do we do the replacement part? We do it by recursively calling. How do we do reverse? So should we remove I minus 1? Should we make I to I minus 1 or j to I minus 1 or both to I minus? Both we should remove reduce by 1. So since we are replacing, both the index would match. We should check the next index afterwards. So we will reduce I and j both by 1. So I minus 1, j minus 1, word 1, word 2. And this will give me the case for replace. Now let's look what will be the case for insert. So if we insert an element in word 1, now this element would match the element in word 2. So what we can do is that we just need to reduce the index j, which is the index for the second word. Why? Because since these two indexes are matched, we just need to reduce the index j for checking the next letter in the word 2. So it would be I will be same j minus 1, word 1, and word 2. Similarly, for delete, since we have deleted an element in the word 1, we need to reduce its index by minus 1 and j will remain as it is. Okay, after this, we can just return answer. And now let's look at the base case. So what if we have reached a case when index I becomes less than 0? What we need to do is just return j+1, which is the number of elements in the other part of the string. So why we return the number of letters in the rest part of the string after we reach index lesser than 0 in the first string? That's because we can just delete the rest of the letters in the string if there is no letter in the first string. That's it. Similarly, if j is less than 0, then return I+1. That's it. Now we need to just call this function, or rather return it. Return recurse. Let's take the size of these. Space I+1. And word 2. I think it should do. Okay, we can see it has passed all the test cases. It has passed all the test cases. Now, will it run for all cases? The answer would be no. It will give either time limit or memory limit exceeded. Okay, so now let's look at the memoization way of doing this problem. So what we do in memoization is we create a array to store all the states. So we will take vector int dp. dp will be initialized by now this dp will be of size n+1 and n+1. And let's initialize it with 0. Now we will pass this in this, remember to put and here we will check if this case, okay, here it will be -1, which will denote that this case has not been visited. If this case has been visited, we will just store this case. And also, since we need to cut the redundant steps, we will check that if this DP, which has been visited before, it can just return the value of the previously stored value, the DP. Okay, now I think it is memorized. Let's check. Okay, okay, yeah, just we need to add DP everywhere. Yes, obviously we haven't decided and defined these two. Int n is equal to word1 dot size, int n is equal to word2 dot size. It got accepted for the test case. Let's run for all the cases and it is accepted. Now let's look at the tabulation code. In tabulation, what we need to do is first create a 2D space. Let's name it DP. We can do it for word 1 dot size plus 1, and for the column part, so this will be the column size. Now let's look at the row size. It will be word 2 dot size plus 1. Now let's look, since we have looked at the base cases, that whenever there is a letter in one word and there is no word, we need to just add the number of words in the other words. So for that, let's create a array starting from 1. Oh, also we can initialize here by giving it 0, because for if both the words are not there, we need not to do any steps. This will be dp I, comma 0. Similarly, we can do it for the row wise initialization of the first row. This will be like this. Now let's iterate for both row and column. And for each of the cell, we need to check if the character at that index matches or not. So for word 1, let's check if I-1 equal to word 2, J-1. If it matches, then for this subproblem, dpi and j will store just the value at the previous state of the dp when these two were not the indexes. else we have three conditions here. What we need to do is to store the value for the current DP by adding 1 to the minimum of DP I minus 1j, DP I minus 1, j minus 1, and DP I comma j minus 1. And finally, we can return the last state of DP, which is n comma n. Let's check if we have done all things correctly. Seems fine. Let's try running it. Obviously, we again forgot to declare the sizes. Okay, it got accepted. Now let's look at it. Look at all the test cases. It got accepted. Thanks for watching.